Welcome to one more video on subRiemannian geometry. In this video, I will present you some examples of Carnot groups. There is a big variety of Carnot groups, and those of large step are complicated. Differently than in the abelian case, starting from dimension 7, for each dimension, there are uncountably many Carnot groups that are of that dimension and that are pairwise non-isomorphic. But let's start seeing some easy examples. Let's start with the first examples. These are the first ones that are very easy. These are Carnot groups of step 1. In other words, these are abelian groups. Okay, so just to revise, for each natural number, where we can consider Rn with commutative operation, the sum. So x, y goes to x plus y. And then the left invariant vector fields are just the constant. So for a given vector, right? So we have the vector field that at every point is constantly equal to v. Okay, so yeah, this Lie algebra is commutative. So this Lie algebra. Algebra is commutative. Namely, if we take two vectors v and w constant, then the bracket between them is 0. And because of this commutativity, we can stratify, and the Lie algebra of this commutative Lie group admits is unique is the stratification with just one stratum, sorry. So the layers, the stratification is called stratum, one stratum V1, which is just the whole Lie algebra. And okay, this is a stratification because V1 in this case is equal to 0. Okay, what is a Carnot distance on this Carnot group? So a Carnot distance on Rn, if you say Rn, I mean Rn with the sum plus, is just the distance function induced on Rn induced by a norm on Rn. So in other words, abelian Carnot groups is the same things of finite dimensional norm vector space. Okay, so these two things. Also, let's stress how we would present this. So in terms of a basis, so in terms of basis for the Lie algebra, so the Lie algebra of this group Rn plus is spanned by the standard constant vector fields dx1 dxn, where in Rn I'm using x1 xn as coordinates. So for which we have that dxi bracket with dxj is always 0 for all ij. And here x1 xn are the coordinates on Rn. Okay, so this was the basic example. Let's make it a little bit less simple. And this is the first example of a Carnot group that is not abelian. This is the Heisenberg. Okay, there are many ways of presenting the Heisenberg group. Here's an example. So as a manifold is, we can write it as the complex number times R, R3, but I prefer to write it like this to use the complex structure, with product zt times z prime t prime equal z plus z prime t plus t prime plus 1/2 the imaginary part of z bar z prime. So this is the conjugate of z. This is the product as complex numbers. And I take the imaginary part in such a way that now this number is a real number. Okay? And here I'm using coordinates zt in c times r. Now this is one way one can easily remember the group structure, but let's see what happens if we take the coordinates x, y, and t. Now with coordinates x, y, t, so in R3, we have, okay, x, y, t times x prime, y prime, t prime equal, I claim that this is x prime, y plus y prime, t plus t prime plus 1/2 x y prime minus y x prime. Okay, let's check if this is the same thing. So what I'm doing is take z equal x plus iy, z prime to be x prime plus iy prime. And now this is the term that I have to look for, which, so let's calculate z bar times z prime. So z bar is x minus iy, z prime is x prime plus iy prime. So let's do the multiplication. Okay, there is some real part. Don't want to calculate it now. What is the imaginary part? Because I only have to calculate the imaginary part. The imaginary part is it comes, so it's this times this, which gives me x y prime, and then this times this, so it's x y prime minus y x prime, which was exactly what I had to put here. Okay. So these are two ways of writing the same product law. Okay, so this is the group that we actually previously saw in this course. Okay, let's check how to calculate some left invariant vector fields. So for example, the left invariant vector field that is an extension of the vector 1, 0, 0 at the identity is Okay, first of all, who is the identity? The identity um, is the element. So the identity of the group is 0, 0, 0 with these coordinates. Okay, so we have to left translate. So we have to so it's x at a point x, y, t is equal to the left translation differential of the left translation for the point x, y, z at the point the identity of the group times the vector 1, 0, 0. And one can do this simple calculation. Is going to be 1, 0 minus y over 2. Okay, right. So let me give you a whole basis. So in Heisenberg group, a basis for the algebra is, okay, we have x 1, 0 minus y over 2, which as derivation you can write dx minus y over 2 dz, dt, using coordinate x, y, t. Y is 0, 1, x over 2, y plus x over 2 dt, and z, which is 0, 0, 1, which is z. So this, so check that they are left invariant. Check also that z is the bracket of x and y. And this is the only non-trivial bracket, only non-zero bracket. In other words, z commutes with x and y. So, 0, z commutes with x and y. All right, so now we can okay, let me write the same structure as a diagram. I can represent, we will represent the Heisenberg algebra, with the diagram x, y, z. To say this symbol, this line means that the vector coming from the, if you bracket the vector on the left arm of this V shape, bracket with the vector on the right arm of this V shape, gives you the vector z. And now, also writing in this way makes you understand that if you take the span of these spaces, then they will generate the span of this space, and then they know this vector, and therefore these two vectors will define first layer V1, and z will define second layer V2. And this will be a stratification. So we have to check that V1 bracket V1 is equal to V2, and that V1 bracket V2 is 0. And therefore this is a stratification of step 2. Let me give you a generalization of the Heisenberg group, which is called the nth Heisenberg group. This is another example, a more general example. So the nth Heisenberg group. So I will now present it a little bit differently. I will present it as a group of matrices. So for an integer n, let's denote it Hn to be all those matrices that have 1 in the diagonal and in the first line you have x1, x2, dot, 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 xn, z. Then you have 1, y1, y2 to yn. This is 0, 1, 1, 0, and all zeros. So this is n plus 1 matrix. So the variables are xi and yi's and z, real numbers. So this is a subgroup of GL n plus 1R. So on the diagonal we have 1. In the first line we have 1 and then x's and then z. And in the last column we have z, y's, and 1. Okay, all the rest are 0. Okay, so this is, one can check that this is a subgroup of GLN. And what is happening is that the algebra of this subgroup is spanned by a basis, let's call it x1, xn, y1, yn, z, with only relation xi, yi, same I, equal to z for I from 1 to n. Some simple properties of this group. So this is called the nth Heisenberg group. So this is step 2, and the second element of the descending central series has dimension 1. This is the span of the vector z. And actually, with this property, then we can characterize what are the Carnot groups with this property. So actually, one can prove that every nilpotent algebra with dimension of the second element of the descending central series of dimension 1. So this is also called the derived subalgebra. If the derived subalgebra has dimension 1, then the algebra, let's give a name G with this property, is of the form some Heisenberg group times the abelian Carnot group Rn. Okay. Okay. This is also a stratified subalgebra, but let me convince you, actually prove it, that every time you have a nilpotent group of step 2, then this is actually stratifiable the algebra. So here's a proposition I want to prove. So every nilpotent Lie algebra of step less or equal than 2 is stratifiable. Okay, let's prove it. Okay, if the step is 1, we just said it's a billion. It's okay. Let's do step 2. So now take any V1 subspace such that it is in direct sum with the derived subalgebra. And set V2 to be the derived subalgebra. Okay, so we have a choice for V1, but V2 is given by this this equation. Okay. Now, the fact that the step is 2 implies that if I bracket this, if I take the bracket between an element here and G, this is 0, which means that V2 is in the center. It commutes with everything. It means that V2G is equal to 0. Okay, so what we get from this observation, we can check that we have a stratification, because V1, V1, what is V1, V1? So since V2 has 0 bracket with G, this is the same bracket of taking GG, which by definition is V2. This is the first condition for a stratification. Second condition, now we have V1, V2. Now, as we said, V2 is commute, so this is 0. And there is, since a step 2, there's nothing else to check. So we got a stratification. Okay. So every nilpotent Lie algebra of step less or equal than 2 is stratifiable. Next example. All the examples that we saw up to now had step 2. Now let's see something of higher step. So we take the strictly upper triangular matrices. Okay, for any natural number, let's G, or maybe N sub N, to be the matrices, have 0 in the diagonal, 0 below the diagonal, and anything above the diagonal. So this is an element in GLN. Okay. The Lie group associated to this Lie algebra is the subgroup of the general linear group that has 1 in the diagonal, anything above and 0 below. GLN. All right, so now this Lie algebra, so this is N, is stratifiable with step exactly equal to N minus 1, with the strata. So the strata Vj is the set of matrices that have 0 in the diagonal, a lot of zeros, and have some things in the jth. So if this is the first, if the diagonal, we call it the first diagonal, then we have the second and third, and this should be the j plus 1 diagonal. So we have yes, we have n minus 1. So the first one is 0. We have n minus 1 parallel diagonals, and each of them will form a layer of this stratification. Okay, so check that you agree with this statement. Okay, now let's go back to the diagram representation of the algebras, of Carnot algebra. So a diagram representation for the algebras, or for Carnot algebras. So you have Heisenberg, for example, we represent that x, y, bracket, z, which means that only relation, only non-zero, only non-trivial, non-zero relation is x, y gives bracket z. Now let's see another example. I call it the angle group. I will first write for you the diagram and see if you can read it. This would be a diagram that I would use to define the angle algebra. Okay, let's see if we can read together this diagram. Okay. So this diagram means, okay, the bracket between x and y gives z. And then the bracket between x and z gives w. X, z, x, z gives w. And these are the only relations. From this way of writing the diagram, we also have a stratification, because you see, if we say that these vectors have degree 1, so they are in the first layer, this one having they are in the second layer, this in the third layer, then one has to check that the bracket satisfies the condition of being a grading generated by the first layer. Okay, so what does it mean? It means, okay, the span of these two vectors will give v1, span of these two, of this only will give v2, and then v3. Okay, so we have to check, let's check if this is a gradient. So v1 will generate everything, because if you perform bracket, you get z, and then with v1 you get w. Okay? And you see, the brackets will be such a way v1 gives something in v2 and only v2. Something from v2 and v1 will give something in v3. And then there is no more bracket. So v4 is equal to 0. Okay? So this is the algebra that is stratified. Pay attention, because if you just write now a random diagram, first of all, this might not satisfy Jacobi identity. Second, might not agree with the grading. We will see later the thing can happen even for nilpotent algebras. But now that we have this diagram, let me give you the example of the algebra that has dimensions for the layers as small as possible. Still, the step might be as large as you want. So these examples are called filiform algebras. Okay, fix an integer. Okay, and we said that an n+1 dimensional Lie algebra, dimensional Lie algebra is said to be filiform if it is stratified as v1 vn, so with n layers, and so the dimension the dimension of V1 is equal to 2, and dimension of Vj is equal to 1 for all j equal to from 2 to n. Okay. An exercise. So if G is Carnot and the dimension of V1 is equal to 1, then G is just R. So for V1, apart from this trivial case, the minimum dimension is 2. So these filiform algebras are the one with the smallest possible dimensions for the stratification. Okay. Examples are the first Heisenberg group, and angle. So this one here. So the first has dimension 2, and then each layer has dimension 1. Now, a fact, I will not prove it, right? So for all the dimensions greater than 6 that are even, there exist exactly 2 filiform algebras. The algebras. There are no more than 2, and there are 2 that are not isomorphic. Otherwise, there is only one. There is one otherwise. This one is called filiform algebra of the first kind. And this is I will present it now. Filiform of first kind. Okay, so G is as a basis x1, maybe it's got x, y, 1, yn, so it's n plus 1 dimensional, with only relation. The bracket between x and yj is equal yj plus 1. So with the diagram, you will see is a very simple generalization of the angle algebra. So if x bracket y1, this will give you y2, and x bracket y2 will give you y3, and so on, until the last one, yn, which is the bracket between x and yn minus 1. You will see that each of these will give a layer, one-dimensional. And of course, like in all these examples, one should really check that these conditions satisfy the Jacobi identity. Okay? I'll give you this exercise. Check Jacobi identity. Okay, so if these filiform algebras in some sense are the smallest in terms of dimensions, then there is also the biggest Lie algebras fixed a step and the rank, because of course the dimension of the first layer could be as big as we want. So this largest one, these are called the free nilpotent Lie algebras. So example, free nilpotent Lie algebras. So let's fix two numbers. So the first one we'll call it rank, and this is the dimension of V1, and the second one is going to be the step. So two natural numbers. Now let's construct the algebra in this following way. So one considers m many abstract generators. So let's call it x1, xm. So they're going to be linearly independent vectors. And then one considers all still abstract. Abstract means that you consider as objects that are linearly independent from the previous one. Abstract iterated brackets, Lie brackets. And then one considers all possible finite linear combinations. Now, of course, this what we have created is an infinite dimensional vector space. Okay. Now we want to kill all the vectors that are iterations of more than s many vectors. Okay? So we mod out by. So also we want a Lie algebra. So let's mod out by the anti-commutativity. The Jacobi identity. And the s plus 1 iterated brackets or commutators. Brackets. Okay. Let's see an example. Okay. But okay, let's give a name to this Lie algebra. So this Lie algebra, this Lie algebra is denoted by fms. So as m generators, s step s. An example. So what is f23? Okay. So to define f23, I take two vectors. Let's call it x1 and x2. Then of them, I have to take the bracket, the first bracket. So I'm going to have x1, x2, the bracket. I will not consider x2 bracket x1 because it's going to be just minus the same vector. And now I iterate. And I consider, so is the first one, this one was the bracket between these two. And now take another bracket and another bracket. So I'm going to have x1 bracket with x1, x2, and x1, x2 bracket with x2. Okay. Now I'm not taking any more brackets because what I want is something as step 3. Okay. So now the Lie algebra, the 5-dimensional Lie algebra or vector space generated by these 5 vectors defines a Lie algebra. This is F23. Now, if the rank, if the dimension of V1 is larger, then one should also remove some vectors according to Jacobi. Okay. Some properties about this free algebra. Facts. So, okay, first of all, FMS is really a Lie algebra and it's finite dimensional. Nilpotent Lie algebra of step S. And actually, this algebra is really stratified, is also stratified by So Vj, this is going to be the jth brackets is the span of brackets of j vectors among the generators. Also possibly repeated. Okay. So in the construction, you see that so we have the first vectors, which we call the generators. Then we have those of degree 2, which are brackets of 2 elements. Then we have those of degree 3, they come from brackets of something of degree 2 to something of degree 1, and so on. So free nilpotent algebras are stratified. Why they're called free is because of this following property. So let me clarify what I mean for rank. So for every nilpotent Lie algebra, let's call it G, we call the dimension of G modulo GG, if you want the codimension of the derived subalgebra, the rank of G. So this fact that I'll explain why they are called the free nilpotent Lie algebra are called in this way is the following: for all nilpotent Lie algebra G of step S and rank M, there exists a surjective Lie algebra homomorphism from the free Lie algebra with that rank and with that step into G. In other words, every nilpotent Lie algebra of step S and rank M is a quotient of the free Lie algebra of step S and rank M. So, in other words, all nilpotent algebras are quotients of free nilpotent algebras. Okay. Let's see some example of free nilpotent algebras. The free nilpotent of step 2. These are easy to describe. These are easy if one uses a little bit of vector analysis. So one consider the K form on Rn. So it's the K forms on Rn. For example, dx1 is one form on Rn, and dx1 wedge dx2 is a 2 form on Rn, and when here I'm using x1, x2, and so on, the coordinates of Rn. Okay, with these forms, we can say that the free nilpotent Lie algebra of rank M in step 2 is isomorphic to the direct sum of the one form on Rm plus the the two forms on Rm, where the product is, if I take a one form and a two form, and the product, take the product with another one form and another two form, this is theta plus theta prime, omega plus omega prime, plus theta wedge theta prime, which now is a two form. So one can prove that this is a free nilpotent Lie algebra of rank n step 2 by uniqueness. It is this one. So in particular, we can also calculate the dimension of Fm2, which is the number of one forms plus the number of two forms. How many times we can choose two elements among m without or to specify the order. Okay. After this, let's see an example instead of a nilpotent but not Carnot Lie algebra. So this is an example of nilpotent Lie algebra but not Carnot. So up to dimension 4 there are none, and then there exist two 5-dimensional nilpotent Lie algebra that are not Carnot, that are not stratifiable. Okay, so the first one, I will still write the diagram like if it were Carnot. So the diagram that I draw would give me the filiform algebra of dimension 5. But now I'm going to add one more bracket. So the bracket between x3 and x2 is x5. Now you see that the new bracket that I draw doesn't maintain the grading, because something of degree 1 with something of degree 2 should have degree 3. Instead, this one has degree 4. Another example is the following. So x1, x2, x3, and then x4. This would be the angle. But now I add one more vector, x5, and I declare that the bracket between x2 and x5 is x4. Okay? So as you see, so the first one had rank 2. Instead, this other one has rank 3. Now this is not in the commutator, right? So this other one has rank 3. So you can try to solve the exercise and prove that these do not admit any stratification. Okay, so far I was discussing Lie algebras. Like here now, I was telling you what examples of nilpotent Lie algebras, or before I was giving examples of Carnot Lie algebras. But I was not, in only a few cases I was really specifying you what is the group, the Lie group. Let me stress that, of course, when one gives you the information of the Lie algebra, has given you also the information of Lie group. How to do that? So, how to go from the information of Lie algebra to constructing the Lie group. So the brief answer is just to use the Bacon-Campbell-Hausdorff formula. Okay, let's see this, how to do it in an example. Let's take an example for which we didn't give the group law, was the angle group. Let me remind you the diagram. So this was the diagram, okay? So from the diagram, you see that this is step 3, okay? So this algebra has step 3. So now what we have to do, we have to look at the Becken-Campbell-Hausdorff formula and truncate it, keeping only at most the brackets of order 3. So the Becken-Campbell-Hausdorff formula for the algebra of step 3 reads like this. So log of x times y is beginning of the sum, then you have 1/2 of the bracket, and then I know the formula and I'll tell you the result. You can go back and try to do it yourself. Is 1/12 of, first you perform the bracket x, y, and then you have y, x. Okay. So taking for granted that this is the Becken-Campbell-Hausdorff formula, what you do? Now you take a vector x and you write it as x1, little x1 plus x4. Y is going to be another vector recorded y. So we are considering exponential coordinates with respect to the standard basis x1, x2, x3, and x4. And now we can perform these brackets, and we can write what is the product in coordinates. So x1 dot x4 y1 y4 is going to be another 4 vector. Okay, I will spare you the calculation. Okay, the solution is this is the solution. So this is the vector, the 4 vector giving the coordinate expression for the angle group. Okay, I hope you like all these examples of Carnot groups. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.